All right, part two. I hope this doesn't go to part three. All right, so we just learned permutations are written this way. That means if you're going to take all the objects and rearrange them as many ways as you can, it's the same as n factorial, but we can always write it this way too. How many different words can you make with these letters? Well, there's 6 different letters. I can do, it'd be the same as saying 6p6, 6 objects permuted or taken 6 at a time, which is the same thing as 6 factorial. And how we do that on the calculator? Well, as long as I'm showing you this, I might as well, it's 720. You can also do permutations this way. You go menu, probability, and look right here, permutations. You get this, where'd it go? Try that again. Menu, probability, permutations. You get that little NPR thing. No, it's not National Public Radio. It's the P symbol, and you're supposed to enter the object that goes on the left side, and then the object goes on the left side. So if I do 6, 6, I get the same thing. Remember that, because it's going to get interesting here in a second. That's 720. This one has 1, 2, 3, 4, 5, 6, 7. So I would just go same thing, but let's enter these as 7s. And that's really the last answer times 7. So that's 5040. 7 factorial, which is 5040. Okay, so this gets more interesting when we don't want to take all the objects and reorder them. So if you only want to order some of the objects within that collection, kind of like when we were doing the bowling, the chess example a minute ago, where there were 16 things we could have ordered, but we only ordered 8 of them. There's that many to choose from, but we're only going to pick this many, and we care about the order. It's this NPR thing. Okay, use the fundamental counting principle to determine how many 3-letter arrangements can be made from the letters of the word graphite. Okay, so the fundamental counting principle is that you can multiply these choices when they're independent. How many choices do I have for the first? There's 8. I have 8 choices for the first letter. I have 7 choices for the second letter. I have 6 choices for the third letter. And realize what that's implying here is the letters can't repeat. That's what permutation means. And it does matter which order I take them in. So GRA is different than GAR. And it's 8 times 7 times 6, whatever that is. But notice that would be the same thing as starting with 8 objects and permuting them 3 at a time. We would get this answer. But man, the calculator's faster. I would use NPR, so menu 5, menu 5, 2, and then you just go 8, 3, bam, it does that for you. And notice that's the same as 8 times 7 times 6, but it's a lot faster, especially as these numbers get bigger. It's a lot faster to use the permutation button. All right, so that's 336. Okay. Oh, and by the way, that's the same as this reduction here. So that would be, this is the definition of the permutation formula. So this would be 8 factorial divided by, if you think about this, 5 factorial, which is 8 times 7 times 6 times blah, 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 all the way down, over starting at 5 times 4 times 3 times 2 times 1, and notice all that stuff would cancel. Let me write that over here. That's 8, this is 8 factorial, all the way down, I'm not going to write them all, over 8 minus 3, which is 5. So 5 factorial. This is how we could tell the computer how to do this smartly. Notice all this stuff would cancel all the way down, and we're just left with the answer we need. So the way to shorten the factorial is divided by a certain section, and that's all I want. List the set of all permutations of these 4 objects if we took them one at a time. Now they want a list, so they're actually supposed to say, well, what are the, it's like list the sample space. If you want one at a time, well, one way you could do that is pick the arrangement that has a W in it. Another one is just this one. Sorry, there's 4, and they are very boring. 2 at a time, well, they'd be things like WX, WY, and there'd be a whole bunch more. If you want to see them all, guess what? You have them on the next page. So let's just go through this. Here they all are with 2 at a time. Listing them is a lot harder than doing the permutations. This would just be, 4. If you're going to figure out how many are in that list, this is 4P2. This would have been 4P1. And that's a lot. But that's different than ask this question, which is actually saying how many, or actually list them all. 4P3, oh my gosh, you had to list all the combinations of 3. That's what they look like. There's systematic ways to do that. I'm never going to ask you to do that on a test. Same thing with 2. It's different if you're taking 2 things at a time if you have 5 to choose from. That's going to be a longer list than, say, this part 1B, where you had 4 to choose from. You're going to take 2 at a time. Let's look at number 2A. 2A, yeah, is way longer than 1B. Each one you're taking 2 things, but you've got more to choose from. 3 at a time, same thing. If I had to pick 3 out of those, look at that. No, I'm not going to ask you to do that. How many are there? 20 and 60. Those answers, that would be from, like a better question for me on a test would be, you have 5 objects, you want to order 2 of them. Or you have 5 objects, you want to order 3 of them. And by order, I don't mean like, menu in a restaurant. I mean, you want to take a collection of 3 of them, and you want to see, you want to put them in different orders. So how many ways can we just pick 3 of these and put them in order? How many different 3-letter words can we spell? And by different, I mean ABC is different than ACB. If you want to count all those separately, it's going to be this many. I keep saying the same thing over and over again, but believe me, it's going to get confusing. So I find success if I tell you the same thing over and over again. All right, and how many ways can 5 different books be arranged on a shelf? So this is exactly the kind of things we're talking about. Now it's a little trickier. We got 5 objects. We're going to take them all and see how many arrangements there are. That's actually just 5p5, which is 5 factorial, which I believe from 5 minutes ago is 120. 3 different paintings from a collection of 8 chosen in a row. Well, didn't we just do 8p3? That's 8p3, and it's some fairly large number that I just did on the last page. By the way, here's the answers again. 336. Oh, yeah, that looks familiar. Part C, a signal consisting of 4 flags. This looks like the beginning of the pretest. Can be made if there are 10 different flags to choose from. So we have 10 to choose from. We're gonna pick 4 of them and put them in order. So that's what that means. Suppose you have different colored flags. How many signals could you make using 2? Suppose you have 4 different colored flags. If you were going to pick 2 of them, you would have, is this getting easy yet? You'd have that many arrangements. If you had 4 and you were going to pick 3, no, P doesn't stand for pick. I know it seems like it should stand for pick. 2 or 3, well, are these mutually exclusive? This is how many ways you can make a signal with 2. This is how many ways you can make a signal with 3. Are those mutually exclusive? Yeah, you can't. You can't have both at the same time. So yeah, let's do some of these in the calculator. It's been a while. So 4p2, that is menu 5-2, right? Yeah. 4p2 is this many. Whoops, 4, 2. 4p3, and notice you can just arrow up and hit enter, and then you can get this back, and you can just change one thing in it. So 12 plus 24 is going to be the answer to the last thing is 36. Here's those answers down here. Number 5. How many different permutations of these 6 letters are there if each letter can be used only once? In other words, we're just arranging the objects. If you can repeat, then we're not really talking about a permutation. We're not talking about taking 6 objects and arranging them. We're talking about, repeating things, and that's not what permutations are. So no repeats, definitely, in all these permutations. How many, if you can use each one only once, how many different permutations of these 6 letters? If the thing ends in E and D, well, if the thing ends in E and D, we don't really get to choose where E and D go. We only have 4 left to choose from. So we only have 4 kind of variable positions. And where are we going to put them? We're going to put them in the other 4 positions. So we have 4 things to arrange from a group of 4. Begin with F and end with A, same thing. You have exactly 4 that you have left, that you have freedom about. Begin with end with a vowel. This sounds like this thing we did before. So there's having A first and E second, or at the end, and having E first and having A at the end. So there's 2 ways to do this, but after that, really, we only have this 4p4 amount of choice. Okay, so that is what that looks like. Check me on those answers. Okay, I know this looks like it's big and, imposing, but it's not too bad. What happens when there are letters which repeat within the same word? So examine this scenario. Let's look at the word rose, and then notice how they're going to change it to Ross and see how that changes things. So with rose, how many different permutations are there? If we're going to take all 4 of them and order them, there should be 4p4 ways to do that. Someone went to the trouble of actually typing this out, from rows forwards all the way to rows backwards. These are all the different ways you can do this. Now, if you changed this rose to Ross, so in other words, you'd have to replace all these E's with S's. Notice what happens. We don't really have that many different ones anymore. Like these first 2, that's not really different arrangements. Like I can't tell the difference between these 2 S's. That's really the same thing. So I kind of don't have this possibility. RSOS, RSSO, like that should probably have another combination somewhere. Oh yeah, look, RSOS, that's got a repeat somewhere. RSSO, that's got a repeat somewhere. ORSS, oh, I've got 2 of those, so I can cross one of them out. Maybe there's a better systematic way to do this. Well, there will be. We'll get there. All right, as we see repeats, let's cross them out. ORSS, I got one there. OSRS, oh, look, there's another copy of that. OSSR, haven't seen it yet, but there it repeats. SROS, haven't seen it, but look, it repeats later. SRSO, I bet there's another SRSO. I don't see it, there it is. Now where am I? SORS, there's another SORS. SOSR, there's another SOSR. SSRO, there's another SSO. And ROS backwards is already getting down here. So how many do I really have left? It looks like I've crossed everything out like half the time. Like I've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's now just 12. There was 24 up here, but if I change one of those E's to an S, so I've got two things that I can't tell the difference about. It's like basically saying every time this is now equivalent to this everywhere. So it's really like what I have to do is divide by 2, which is exactly what happened. Let's see if that continues. If we replace the other vowel with S, so I really have 3 that I can't tell the difference of. Look, this entire column is the same, so I don't care about those. Actually, these are the same too, aren't they? And then I have SRSS, so I don't care about any of other SRSSs. SSRS, SSRS, SSR, like there should be 3 of all these, right? SSRS, what's the next new one? SSSR, sounds like a former country. Okay. And then there's another one of those. SSRS, I think I already had, I forgot 2 of those. And SRSS, I think I already had. So really, there should only be 4 of these, right? The R can be the first one, the second one, the third one, or the fourth one, and that's it. Ooh. Do I just have 4 now? Yeah, I just have 4. So I had to divide by 2. If a letter pattern appears twice in a word, we divide the total number of arrangements by how many ways you can arrange those repeated letters. So notice here there were 3 ways to arrange the S's. So really, I had to divide the original by 3 factorial, because those 3 arrangements now, there's 3 factorial of them, they are all equivalent. I can't tell the difference between them. So they're going to show up more in the sample space, but I don't count them as different arrangements. In the fact where I had 2 that were indistinguishable, I had to take the original and I had to divide it by 2 factorial. Okay. The question again is just how many different arrangements are there? So the number of permutations of n objects where you have A of the same of one type, B of the same of another type, etc., can be represented by this equation. So how many different looking words can we make of this? Oh, and we're talking about total permutations. So 1, 2, 3, 4, 5, 6, 7. I have 9 total permutations I could start off with, but I have to divide that by whatever repeats I have. So the V's repeat, there's 2 V's. Anything else repeat? I think that's it. So I can stop right there. Am I right about that? Yeah. So there's only it's gonna be half of 9 factorial, whatever that is. This one has 12 letters in it. How many things repeat? Well, there's 2 M's. There's 2 T's. Anything that doesn't repeat, I don't have to, gets to be its own sort of unique placeholder. So I don't have to divide by anything. So I counted for the M's. I counted for the T's. Anything else I have to count for? Oh, A's. There's 3 A's. So that reduces the number a lot because it makes 3 indistinguishable things that are going to happen in that one. I'm not going to finish this in 2 videos. I think I got them all there. Okay, we can get a little bit farther in this video though. All right, how many arrangements of the word puppies can be made under each of the conditions without restrictions? Okay, so how many were we supposed to have in the first place? Well, that's 7 letters, but there's some indistinguishable letters. Like I have 3 copies of P. I think that's it. Each arrangement begins with a P, so, sorry, before I do that, this is the same as 7 times 6 times 5 times 4, if you think about it. Yeah, if you had to write that out. Each arrangement begins with a P. All right, so it's like you might as well just take 1 P out of the list, and it's just I have this left to deal with. So I have 6 things to arrange, but there's some that are indistinguishable. I have 2 of the P's that are indistinguishable. The first 2 letters are P, so it's not like taking 2 out of there, and now I have 5 totally different things left to arrange. If all the P's are together, the way I would do that was let's just consider the P to be 1 letter, because it's like 1 block that I can't really break up. So it's exactly the same as, now I really have, if you think about it, I have 5 letter blocks. I have I, E, S, O, and the triple P. And I have to put the triple P together, so it's like another letter. The first letter is P, and the next one is not P. So how many choices do I have for the first thing? Well, let's just take 1 out. That's just kind of over. The next one is not P. Oh, this is kind of a pain. I have 4 choices for the next letter, and then how many choices do I have after that? After I do that, I've got, so there was a not P. I have an SIE, for example, and then I have 2 indistinguishables. So 1, 2, 3, 4, 5 things left, but 2 of them are indistinguishable. Okay, I'm going to stop there. Okay, here comes part 3.